So in problem 21, we've got this subset of matrices from the vector space of 2 by 2 matrices. And we want to show that this set H is a subspace of M 2 by 2. And we have a few options. But before we get into the options, we want to know what it means to be an element of H. So by writing the matrix this way, the defining characteristic of the matrices in H is that they all have a 0 in the second row, first column. That's the defining characteristic. A, B, and D are not related. It's this second row, first column entry that's always a 0. That's the defining characteristic of elements in H. So elements in H are 2 by 2 matrices with a 0 in the second row, first column. Now note that A, B, and D can all be 0 as well. It's just that this entry, the second row, first column entry, that has to be 0. A, B, and D can be whatever they want, but we have to have a 0 there. I almost circled it, and that's what I usually use for pivots. So A, B, and D can be anything, including 0. So sometimes we assume too much when we look at a form. It's like, oh, this could be the only 0, but that's not the case. This is 0, the other 3 can be anything that they want, and there's no relation between those 3 entries. So there are a couple of ways that we could show that H is a subspace. My favorite way is to show that H is the span of a set of vectors. So if we could show that H is the span of a set of vectors, then H is a subspace. That's one option. So our options. So our options for showing H is a subspace. Our first option for showing H is a subspace is to use the definition of a subspace. It contains the 0 vector, it's closed under vector addition, and closed under scalar multiplication. So the first option would be to show 1, that it contains the 0 vector. 2 is closed under vector addition. And 3, it's closed under scalar multiplication. The other axioms of a vector space we inherit from M 2 by 2. So the only things that we need to show for a subspace is that it contains the 0 vector, is closed under vector addition, and closed under scalar multiplication. That's one of our options. Our other option, which is the fancier one, and technically at this point in the chapter we don't have it yet, our other option is to show that H is the span of a set of vectors. So find a spanning set for H. This one is my favorite one because once we have a spanning set, we can whittle it down to a basis. This is a little bit futuristic. So if we were just starting off in chapter, actually no, I do the same thing even when I start off in this chapter. So all we need for a spanning set is something that we can have for the A here, a B here, and a D here. So if I look at this matrix, A, B, 0, D, I can say it's A times this vector, 1, 0, 0, 0, plus B times this vector, 0, 1, 0, 0, plus D times the vector 0, 0, 0, 1. And so these three matrices form a spanning set for H. H can always be written as a unique linear combination of these three vectors. So we would say H is the span of 1, 0, 0, 0, 0, 1, 0, 0, and 0, 0, 0, 1. Therefore, H is a subspace of M 2 by 2. Scroll. So this is always my favorite. Find a spanning set. That to me, that's my favorite theorem from this particular chapter. Find a spanning set and you got yourself a subspace. Moreover, you're already taking that next step onto describing everything in the space as a unique linear combination. Even better, the set that we described here is a basis for H. Technically, at this point in the section, I don't think we have, oh wait, no, exercise 11 is all about finding a basis or finding a spanning set. If we want to show the three things that it contains the zero vector, we would have to just point those things out. So clearly the zero vector has a 0 in the second row first column, so 0 is in H. If we add two matrices of this form, the second row first column entry will be 0, plus another second row first entry will be 0, so the sum will have a 0 in that entry. If I multiply this by some scalar k, we'll still get 0 in the second row third column. So we could show those three things, but we would have to do a little bit more writing to get that out. So if we want to show, so let's just write that out. So let's let A and B be elements of H, and let's let K be any scalar. I guess technically we know our scalars are coming from the field of real numbers, but K be any scalar. So since A and B are in H, they have a 0 in the second row first column. So since A and B are in H, A will have a 0 in that entry in the second row first column, and B will also have a 0 in the second row first column. We don't know what the other three are. We can't say that they're the same, so I'm just going to label them. This will be A1, B1, and D1. And B will have an A2, B2, and D2. So if I look at A plus B, I get A1, B1, 0, D1, plus A2, B2, 0, D2. I end up with A1 plus A2, B1 plus B2, 0, D1 plus D2. And so we can see that since A plus B has a 0 in the second row first column, this is an element of H as well. A and B are in H, their sum is in H, therefore H is closed under vector addition. Because the sum, if I take two vectors with a 0 in the second row first column, their sum will have a 0 in the second row first column. So there's an example of what we would have to do to show H is a subspace by using the three things. Contain 0, closed under vector addition, closed under scalar multiplication. But the best thing is to find a spanning set. If we can write a spanning set, then we should write a spanning set. That's most efficient. So this second one is a partial version of the first one. And I showed 2. Any questions on 21? So the key thing here is identifying what it is, what's the defining characteristic of the elements of a subset, and then use those. So one of the reasons that I didn't want to go over the 3 things for problem 21 is that we have to use the 3 things for problem 22, which was also a question under that's been requested. There's no difference. A subspace is just a subset that is also a vector space. So F is a fixed 3×2 matrix. So F is a fixed 3×2 matrix, and H is a set of all matrices A in M2×4 such that FA equals 0. So H is a set of all matrices A in M2×4 such that FA equals 0. The 0 matrix in 3×4. Okay. And we want to show that H is a subspace of M2×4. In this case, we do not have the ability to write down a basis for this space because we don't know the specifics of the matrix F. Since we don't know exactly what F is, we can't write down a basis. Since we don't know F, we're going to have to show the 3 things. We can't write down a basis or a spanning set. So we're going to have to show the 3 things. We're going to have to show that the 2×4 0 matrix is in there, that if we take 2 matrices here, it will be their sum will be in the space, and a scalar multiple of any vector in the space will be 0. So here is the defining characteristic. This is what it means to be in a space. This is where I really don't like the way I phrase things. I really don't like that they chose F here for the matrix, because a matrix is in this space if F times that matrix is 0. This is what it means to be in H. So so the problem is I usually say you are in H if FU equals 0. I just never, that's a bad phrasing, but oh well. So this is the defining characteristic. This is what it means to be in H. So a matrix is in H if F times that matrix is 0. If a matrix is in H, then F times that matrix is 0. We can use it to characterize everything in this subset, and we can use it to show that something is in the subset. So we have to show 3 things. Notice that the 2×4 0 matrix is in H. 0 is in H since F times 0 is equal to 0. So that's the first one. This does contain the 0 vector. And in this case, when I write 0, we are talking about the 2×4 0 matrix. So, all set there. That's number 1. Number 2, I have to show that if I have 2 matrices in H, then their sum is in H, too. So let's let A and B be elements of H. Since A and B are in H, F times A is 0 and F times B is 0. That is what it means to be an H in this problem. If I multiply F times A plus B, I can use properties of matrices. In particular, multiplication distributes over addition, because that's one of the properties of multiplication. This is equal to FA plus FB. Multiplication distributes over addition. This equality is since multiplication distributes over addition. FA is equal to 0 and FB is equal to 0, so we get 0. Therefore, we can conclude that A plus B is in H, because F times A plus B is 0, and that's what it means to be in H. Therefore, A plus B is in H. Now I need to show that the H is closed under scalar multiplication. So, this is 3. I'm going to say, let's suppose that we have some vector or some matrix in H and some real number. If A is a matrix in H, then F times A is equal to 0. That's just how we define H. So if I do F times K A, properties of a vector space tell me that if I have a scalar multiple of a matrix, I can just multiply the matrices first and then multiply by the scalar. And since FA is equal to 0, I end up with 0. Therefore, KA is in H. Therefore, H is closed under scalar multiplication. And check the vector space axioms for there. Therefore, we can conclude H is a subspace of M2 by 4. Any questions? So 21 and 22 are good problems because you can either use the definition of a subspace to show that we have a subspace like we had to do in 22, or if we can find a spanning set, then we should do that because it's a lot easier to find a spanning set. Right. In problem 33, we want to employ the same strategy. H and K are subspaces of a vector space V. The sum of H and K, H plus K, is a set of all vectors in V that can be written as the sum of two vectors, one in H and one in K. We're going to show we can do this. We're going to use the same technique. We can't write a spanning set for H and K, so we're going to have to use this technique. Contains the zero vector. If I take the sum of two things in H plus K, their sum is in H plus K. If I take anything from H plus K and multiply by a constant, I get a vector in H plus K. So Once again, this comes down to recognizing how we characterize the elements of our subspace. How do we define the elements of our subspace? So H plus K, well, let's set everything up. H and K are subspaces of vector space V. H plus K, the sum of H and K, is the set of all vectors W in V such that U plus V, W is U plus V for some U in H and V in K. So to build the vector space H plus K, we take something from H plus something from K. And we want to show that H plus K is a subspace of V. All right. So we have to show three things. We have to decide if 0 is in H plus K. Since H and K are subspaces, 0 is in H and 0 is in K. So the first thing, since H and K are subspaces of V, 0 is in H and 0 is in K. Therefore, 0, since 0 equals 0 plus 0, I'll throw that in there. Let's get all the details. So if I take 0 from H and the same 0 from K, they're not different zeros. We only have one 0. But since 0 is in H and 0 is in K, 0 can be written as the sum of a vector from H and a vector from K. 0 must be an element of H plus K. First step done. H plus K contains the 0 vector. So 2. I need to take two different vectors from H plus K. So I'm going to say, let W1 and W2 be two vectors from H plus K. Now I'm going to write down what it means for W1 to be in H plus K. So W1 is equal to V, let's say, I'm going to use the same notation up here. U1 plus V1, where U1 is in H and V1 is in K. I spelled K wrong. And W2 is going to be U2 plus V2, where U2 is in H and V2 is in K. This is just saying what it means to be in H plus K. If a vector is in H plus K, it's the sum of some vector from H plus a vector from K. So if I look at W1 plus W2, that's equal to U1 plus V1 plus U2 plus V2. And since vector addition is commutative and associative, this is equal to U1 plus U2 plus V1 plus V2. So this is since vector addition is commutative and associative. Order and grouping don't matter in vector addition. But since H and K are vector spaces, are subspaces of V, H and K are both closed under vector addition. So since H is a subspace, U1 plus U2 is in H. And I ran out of space. Since H is a subspace, I'll weigh that down. Since H is a subspace, U1 plus U2 is in H. Also, since K is a subspace, V1 plus V2 is in K. To be a subspace, you must be closed under vector addition. Therefore, W1 plus W2 is in K plus H. H plus K. It's commutative, but I don't want to just change the name. So H plus K is closed under vector addition. Part 3, I need to grab a vector from H plus K and some scalar and show that the subset is closed under scalar multiplication. So 3. I'm going to just grab a vector from H plus K. So let's let W be an element of H plus K. And let K be some scalar. Since W is in H plus K, W is U plus V, where U is in H, I should say for some. That's the phrasing that we use at the beginning. Force, it doesn't matter. So W is U plus V for some U in H and V in K. That's what it means to be in H plus K. If I multiply K, K times W, that's just going to be K times the sum of U plus V, and that will just be K times U plus K times V. This is just using vector space axioms. Since H is a subspace, since H is subspace, KU is in H. Since, oops, not sign. Since K is a subspace, KV is in K. Therefore, KW is in H plus K. Because I have written W from H plus K times K, which is a real scalar. Shouldn't use the mortal constant because of the K's. Oh well. I've showed that W is the sum, K times W is the sum of something plus H and something plus K. So that's what it means to be in H plus K. Therefore, H plus K is subspace of V. And we're concluding the subspace part. Any questions? In the second part, We can show that H is a subspace of H plus K because 0, everything in H looks like a vector in H, U plus 0. And K is a vector space, so K contains the 0 vector. So we could do the second half of the problem is we just need to observe that H and K are subspaces, so they contain the 0 vector. Any questions on 33? How's everybody? Y'all are very quiet today, but no more quiet than normal, so. Yeah, you turn in homework until homework closes. All right, I'm going to pause the video for homework 4.1, and we'll switch over to section 4.2 homework.